Hello everyone. In this presentation, we will briefly go through a journal paper named Efficient Secure Building Blocks with Application to Privacy-Preserving Machine Learning Algorithms, which is a joint research of Artem Chamili, Erkay Savaş, and Albert Levy, all from the Department of Computer Science and Engineering at Sabancı University in Istanbul, Turkey. Scope of the problem. Today, we have different entities such as hospitals, cybersecurity companies, banks, and so on, that collect data of the same nature but often with different statistical properties. It has been shown and proven that if those different entities merge their privately collected datasets to train a machine learning model, they would often end up with a trained model that outperforms the human experts of the corresponding fields in terms of classification accuracy. However, there is a drawback. Due to judicial, privacy, and cost reasons, no entity is willing to share their data with the others. We have a similar scenario during the classification or inference stage. Even if an owner or cloud server has an already trained model and there's a user that has an unclassified query that he wishes to classify, still we have those privacy concerns. Namely, the user doesn't want to reveal any information about his query, which might contain sensitive information related to him, such as his credit card number or private medical records, and so on, and neither does the user want to reveal his final classification. The owner of the trained model also wants to keep this model private. To this end, we propose a solution which is based on privacy-preserving training and classification for the first and for the later case correspondingly. To be more specific and precise, the security requirements for the privacy-preserving training stage are the following. 1. No party learns anything about the contents of any dataset owner. 2. All of the parameters of the finally trained model should be kept secret, preferably in encrypted form. 3. The trained machine learning model should have the classification accuracy as would a non-privacy model have, which is trained over the merger, the union of all of the datasets combined. And 4. Avoid common attacks such as eavesdropping, collusion attacks, and so on. On the other hand, the security requirements for the privacy-preserving classification stage are the following. 1. Query privacy, so that the server or any other participant isn't able to extract any information about the user query. 2. Classification privacy, so only the user learns the final classification result and no one else. And 3. Trained model privacy, so that the user learns nothing about the trained model, neither the user nor any other participant. In order to achieve this, we propose novel secure building blocks based on arithmetic circuits and apply them to privacy-preserving machine learning algorithms. In this paper, we exclusively deal with Naïve Bayes training and classification models only, and in the future we plan to extend those blocks and add other new blocks and use them to deal with the k-nearest neighbor, support vector machines, decision trees, logistic regression, deep neural networks, and so on. Related research. In this table, we give a review of different schemes, close to 20 different schemes, which deal exclusively with Naïve Bayes, be it privacy-preserving training or classification or both, and compare them with different security properties and characteristics which are closely to, well, there are dozens of such properties. Our scheme is shown to implement all of those security requirements and properties, and from those dozen properties I'm going to emphasize only 2 of them. Namely, to the best of our knowledge, our scheme is the only one that during the training, the privacy-preserving training stage, it also keeps the trained model secure or private, so no party is able to retrieve any information about it. On the other hand, and again, to the best of our knowledge, during the privacy-preserving classification stage, our scheme is again the only one to deal with active malicious users during the classification. Of course, we are talking about the Naïve Bayes, for the Naïve Bayes case. Preliminary sent notations. Naïve Bayes is a supervised machine learning technique used for classification. In our case, the dataset has f+1 columns. That means we have f features and there is one class column, and nt rows or instances, where nt stays for number of transactions. All of the features are named as f1 through ff, and they are basically sets which have a certain number of values, which are named as from v1 fi to vfi fi, where this fi in double vertical bars is basically the cardinality or number of elements of feature fi. And the index I is basically the index that throughout the paper and this presentation we are going to use to iterate through features. M is the index that we will iterate through feature values for all of the features fi or certain feature fi. For the classes, each of the rows can, for the attribute, for the class column, or for the class cell, it can take only one of the values from C1 to CC. So this is the class set. So we have C such classes, which we are going to denote them as CJ, and J, of course, is going to be the index that throughout this paper and throughout this presentation and the paper we are going to use it to index classes. So J is between 1 and C. Now, by NCJ, we denote the class frequencies. By this notation, we denote the joint feature value class frequencies. BCJ is the class probability, and with this we denote the conditional probability. With this notation, we denote the conditional probability of a certain feature value we denote the conditional probability of class and feature values. And if we have all of those probabilities, class probabilities and conditional class feature value probabilities among all of the features and all of the feature values and all of the classes, then we have the trained model for the Naïve Bayes case. In that case, if we have an unclassified query x, which is equal to which has features from x1 to xf, such as xi is element to fi, and we want to classify, that the classification is going to be done in the following manner. Basically, if we are going to use again conditional probabilities, and if we observe this query, we are going to find the conditional probabilities for all classes, the posterior probabilities of this feature, the observed feature, to belong to a certain class CJ, and of course we're going to do it for all of the classes, C classes, and see which one has the highest posterior probability. If we use the Bayes formula, then this term can be expanded into this. Then furthermore, naively assuming that those features are independent from each other, then this term can be written in this fashion. If we substitute it in the formula, then we get this expression. Furthermore, knowing that among all of the classes, the probability to observe the unclassified query is the same, so we can basically delete it and not take it into consideration, because we don't care about the exact probabilities, posterior probabilities, but we care about the posterior probability, which is the highest among all classes, from all the classes. So we can, if we delete this term, and we know that, furthermore, knowing that the logarithm is a monotonically increasing function, then this term can be expressed in this way. If for xi we substitute the corresponding value of the corresponding feature, and knowing that when we deal with privacy-preserving classification, especially with encrypting data, we often want to encrypt them in integer form, while those probabilities are not integer. So basically we want to integerize them, and we do it by multiplying them with a constant k. So basically from this one, and substituting for those two expressions over here, we get this expression. Furthermore, if we assume that those global frequencies for the classes and the feature value, joint feature value and class frequencies or counts, if they are obtained from different data sets, then for the class frequencies, we can write the following expression, where n superscript k cj is basically the class frequencies at a certain dataset owner k, and k is from 1 to n because we have n such datasets owner. So this is for class frequencies. For the number of transactions, we have the same formula basically. The global number of transactions is the summation of the number of transactions at local datasets, where ntk is the number of transactions at dataset k, and k is again, it's going to be the index that we throughout the paper we are going to use it, and throughout this presentation we are going to use it to iterate through dataset owners. And the similar goes for the joint feature value and class frequencies. The FV somewhat homomorphic encryption scheme. It's a public key crypto system which is based on the hardness of ring learning with errors, and it allows two homomorphic operations on the ciphertext without decrypting them, which are addition and multiplication. However, since it is a somewhat homomorphic encryption scheme, such a number of operations is limited, especially the number of multiplications, and the number of consecutive homomorphic operations that are allowed on the ciphertext without decrypting them is called the depth of the circuit. Here the plaintext and ciphertext are polynomial rings with modulus x to the power of n plus 1, and their coefficients are integers modulo t and q correspondingly, such that q is much greater than t. If n, t, and q are chosen properly, then we can apply the Chinese remainder theorem, which in turn enables components or index-wise or coefficient-wise homomorphing single instruction multiple data operations over the polynomial coefficients. We have some notations here. With m underline v we represent a vector of integers, m underline p we represent a plain text, with m in or any notation in square brackets. It's basically, this is how we represent the ciphertext. And here we represent the homomorphic encryptions. Basically here we have addition of two ciphertexts, and their addition gives us another encryption of a ciphertext, which is the encryption of their summation on plane. The same goes with the multiplication. Chinese remainder theorem can also allow us to rotate the ciphertext due to the automorphism of the reducible polynomials through which we can express this guy over here, the polynomial modulus. The rotation in the pseudocode is written as a function rotate, while in the pictures, in the figures, is going to be written with arrows, and it can be to the right and to the left. Just as we can add ciphertext, we can add the ciphertext and plain text. And here we show the SIMD way, single instruction multiple data way of adding two different ciphertexts. So here we have one ciphertext and their coefficients, another ciphertext and their corresponding coefficients. If we add A and B, for free basically, we are adding n such components component-wise or index-wise. The same applies for the multiplication as well. And here we have the rotation where we rotate to the right for two slots the coefficients of this ciphertext A. System architecture and participants. In our system we have 4 different constituents or participants. The first one are dataset owners, which are owners of privately collected datasets, and they wish to use those datasets to train a Naïve Bayes model in privacy-preserving fashion. We have n such dataset owners. Then we have one participant, which is called the aggregation cloud server, or its abbreviation is TAX, which is a powerful server where all the computation is being done, and furthermore, we keep our trained model at TAX. Then we have the encryption-decryption server, or EDS, which is the only participant in our scheme that has public crypto system key. So basically it has a private and secret key, and all the encryptions in our protocols and algorithms and schemes are going to be done with the public key of EDS. So EDS is basically the only participant that can decrypt such ciphertexts. Finally, we have users, and users have an unclassified feature query X, and they wish them to classify it in privacy-preserving fashion, having in mind the security requirements that we already mentioned. Threat model or adversary models, we assume that all the participants are in the semi-honest model, which means that, or honest but curious, which means that they follow the protocol, but on the background try to infer some data or info that they're not supposed to. We also assume that TAX and EDS never collude or cooperate with each other in any of the algorithms. During the privacy-preserving training, up to n out of n data set owners can collude. Then during the user-centric classification, the user is a bit more malicious than a semi-honest model. Basically, it's an active malicious user which can implement the substitute and compare attack as it is given in reference 33 or 34 of the paper. And finally, for the server-centric classification, we introduce malicious users. We deal with them. As we mentioned, for the first time, we do it in our schemes for the Naïve Bayes case. Secure building blocks. Secure sum of blocks of NS slots is our first algorithm. It's better explained in this figure. Basically, this algorithm allows us to find the sum of blocks of NS slots, and at the end of executing this algorithm or secure block, the sums of blocks of NS slots will have their sum at the first slots of the corresponding block. This is our input ciphertext, and we find the secure sum in the following way. So we just rotate the input ciphertext from one slot to the left, then we add up those ciphertexts in SIMD fashion to get this result. Then we rotate it to the left for two slots, we add them up to get this ciphertext, then we rotate it for 4 slots and add it for 8 slots, for 16 slots, etc. And finally we have the desired output, which is having the sum of blocks of NS slots at the first slot of each block accordingly. Apparently we have log NS additions and rotations for this algorithm. Secure random ciphertext permutation. It's again better explained the algorithm in this picture. Firstly, we assume that the input ciphertext is organized in the following way. We have C data slots which we are interested in, and we name them as A1 through AC, and those data slots are separated from each other by NS slots. C and NS are one of the parameters, one of the inputs of our algorithm. Furthermore, we firstly rotate to the right this ciphertext by R1, which is another input, and R1 is a multiple of NS. Then we divide those C data slots into blocks of M slots, and for each block we basically apply simultaneously in SIMD fashion the random permutation inside of that block. Here M and that random permutation is done according to the vector K. Here M and K are random, so the number of elements per block M is random, and the way how they are going to be permuted is also random and is kept secret. Here we show it for M being 3 and K being 2, -1, -1. That means that the first elements of each of those blocks of M data slots is going to be rotated by 2 NS slots and put to the corresponding place. The second one is going to be rotated by -NS slot, so by my NS slots to the left, and the third one also, and this is done for all of the slots, for all of the blocks. Finally, after we do this, we just rotate the ciphertext to the right for R2 slots, and R2 is again a multiple of ns. Now the way that we do those permutations inside of the block is shown in this paper, having in mind the case when m is 3 and the permuting vector is k. So basically, if this is our input and if we want to permute it in the way that we just showed, we construct m plain texts, and in each of the plain texts we put one so for the first plain text we put one at the first slot of each block. Then in the second plain text we put one at the second slot of each block, and so on. After we do it, we multiply those plain texts with the input ciphertext, and then we rotate them according to the corresponding index of the permutation vector k. So the first one now in our case is going to be the first data slots of each block are going to be rotated by 2ns, because this is what the vector k says. The second and the third data slots are going to be rotated by 1ns to the left in this case, because k was -1 and -1. Then we'll get those ciphertexts over here. When we add them up, we are going to get the desired outcome. This is the random ciphertext permutation algorithm. The inverse of this algorithm is the following. It's simple, basically. Firstly, we just execute the rotation not to the right but to the left for R2 slots. Then we do the inverse permutation inside of the blocks of m slots, and after we do it, we just rotate that result to the left for R1 slots. Secure comparison: if we have two ciphertexts A and B with their coefficients or integers, I call it integers, from A1 to AN, or B1 to BAN correspondingly, and when we want to compare them index-wise, component-wise, then this is what we do. A minus B multiplied by random plain text, so this is a random plain text, and basically all of the elements of this random plain text are greater than 0. Now, if for all of the indices, let's call them AI minus BI multiplied by RI, if this is positive, that term is positive, that means that in that particular component index, A was greater than the counterpart B of the same index, basically, and vice versa. However, there's a drawback with this secure comparison protocol, namely, if we execute it several times, and if A minus B or one of the R's happens to be a prime number, then we can factor A minus B of any of the indexes, and factoring them basically means we know exactly how much A minus B is, and we don't want to do that. That's why we advise to use this comparison protocol only once. So we call it one-time comparison protocol. In order to avoid those drawbacks of this protocol, we propose this one, which is similar to the previous one, but after multiplying it with a random number, we just add another random number h. Again, those random numbers R1 through Rn are greater than 0, all of them. However, the corresponding values of h can be negative numbers, but their absolute value is smaller than the corresponding R value. So basically h1 can be -1, but a negative number, but its absolute value cannot be greater than R1, and the same goes for all ages. So this is what we get slot-wise or component-wise, and of course, if any of those terms is greater than 0, that means that the A index is greater than the corresponding B index, and vice versa. Secure comparison of all data slots. It's again better explained with this. So this is the pseudocode, and it's better explained with this figure over here. Again, here we assume, and this is the input of our algorithm, that we have C such data slots which we are interested in, well, that we have enumerated them from A1 to AC, and they are separated from each other by NS slots. And we want to compare all of them using the secure comparison algorithm that we just saw. We do it in the following manner. So if this is our input, then we just rotate it to the left for NS slots, and we call this ciphertext temp. So we subtract input with the temp, and we store the result in a temporary results 1 ciphertext, and then we just rotate the ciphertext for C/2 minus 1 slot to the right. Again, this temp is rotated for NS slots to the left, and now we again subtract the input with the new temp, and here we get and store the result in temp result 2, which in turn is rotated to the right by C/2 minus 2 slots. We do so for C/2 slots, and finally all of those temp results are added up to get this vector over here. Now, in order to have the effects of secure comparison, we multiply this guy with random p and random h, as we already explained. And finally, with random p first, or random plain text, and then add the random h in the way that we explained. And finally, we get this vector where we have the secure comparison for all of the data slots. Now, the data slot that has all of the secure comparison positives, that means that it's the maximum one. It's the index that contains the maximum integer. The one that has all the positives except one negative is the second in order, and so on. We are going to use Scott's algorithm for the secure maximum algorithm. In this scenario, we have two parties, party A and party B, where party A has an encrypted input ciphertext, as we already explained in this way, and party B has the key to decrypt it. And at the end of this algorithm, we want party B to have the index of the maximum integer and nothing else. So we do it in the following way. First, the input is randomly permuted. Then in this permuted input, we securely compare all of the data slots, and we send this result to party B. Party B receives it, decrypts it, and finds the index of the maximum of this permuted input. And that is the index basically for which all of the comparisons are positive. Then party B constructs a vector where everything is 0, except for this random max index, which is 1. And he encodes and encrypts this vector and sends it to party A. Party B receives it. Now party A receives that and executes the inverse cipher random text permutation and sends this result to B. B receives the result, decodes and decrypts it, and finally he gets the index which is basically the index of the maximum integer. So this is the secure maximum protocol, and the last secure building blocks that we are going to see is Cpack. In Cpack, basically we take an input vector, we take a vector of m ciphertexts, and in all of those ciphertexts we assume that we have NL data that we are interested in. It's better illustrated in this figure over here. So this is my input vector, and we have NL data that we are interested in all of them. So starting from the second input vector, we just rotate it to the right by NL, and we get NL slots, and we get this result. Then the third one is rotated by 2NL, so we get this result, and so on. Finally, those guys are added up, and here we have them packed in a single ciphertext. Now let's continue with privacy-preserving training of naive Bayes models. But before that, I just want to briefly show you the codes in C++ for those building blocks. So we have a header file, a corresponding CPP file of that header, and here we have the implementations of them. Basically, We are going to upload those codes most probably in GitHub, and you'll have the link in the description below. Now we can continue with the privacy-preserving training of Naïve Bayes models. At phase 1, basically all of the dataset owners simultaneously in parallel execute phase 1, and this is what they do. They construct the frequency vector, which for all features, for all feature values among all classes, all of dataset owners do the following. This is how the feature vector looks like. We show here a portion of a certain class CJ at a certain dataset owner CK, how it looks like, the frequency vector for that class. So basically at the beginning of the class we just put the local frequencies of the class CJ at dataset owner K, proceeded with the features and feature values in order. So here we put in order the joint frequencies of the class CJ and the corresponding feature values of at dataset owner K. So this is for class CJ. In similar fashion, we do it for all of the classes from C1 up until CC, and when we get the frequency vectors of all of the classes, we just encode and encrypt it to obtain the training vector at dataset owner K. All of the dataset owners do the same, and after they encrypt and encode and encrypt their training vectors, they just send it to TAX, where we continue with the second phase. Basically, TAX receives all of those training vectors and he sums them up. So from the local frequencies, he finds the global frequencies. Then TAX constructs a random vector and multiplies this global training vector with this random vector to obtain the random GTV, and sends this random GTV to encryption-decryption server, and in order to overlap with phase 3, so while encryption-decryption server is doing its job in the third phase, the TAX server basically constructs the random logs of inverse prop vector, basically for all of the feature values among all of the classes. Using those formulas, we construct this vector and we put the corresponding component or integer in corresponding slot. Now in phase 3, the encryption-decryption server obtains the random GTV. He decodes and decrypts it and calculates the random trained model, basically for all features, all feature values among all classes. This is what he does, and he puts those components integers in the corresponding slots. Basically, this represents the random trained model, which the encryption-decryption server sends to TAX, and TAX finally receives this random trained model, and using those formulas, basically for all features, all feature values, and all of the classes, he removes the randomization by adding the random trained model that EDS sends with the random logs of inverse prop that he constructed to finally get the trained model. Basically, when we add those terms, I'm just going to show it for the class probabilities. We just remove the term RNT and the term RNCJ, which are the random numbers, and what we get is the following, which is basically the class probabilities. We do the same with conditional class feature value probabilities. So this is the training phase, and the trained model is now kept at TAX in encrypted form. Now let's proceed with the privacy-preserving classification. We will first continue with the server-centric classification. Phase 1 is done at the user, and user has an unclassified query which looks like this, where xi's are elements of fi, and if a certain xi is equal to certain feature value, then we put 1 to that corresponding slot, otherwise everything is 0. We do it for all of the features and all of the feature values. Basically, it's better shown again with pictures. This is the portion related to class CJ. In the first slot we put 1 because we're going to need it to multiply it with the class probability. Then we have the slots for all of the features and all of the feature values in sequence. If x1 is equal to the value of the feature, or to one of the values of feature 1, we put 1 over there, otherwise everything else remains 0. We do the same with all of the features, as I mentioned, for all of the features and all of the feature values. So this is only the portion which depicts, shows class CJ. We do the same. Basically, we replicate this vector C minus 2 times to get the following. So this is the query vector, and we have the same query vector for all of the C classes. Finally, we encode and encrypt this query vector to get the encrypted query vector, and the user sends it to TAX for phase 2. Now TAX receives this encrypted query vector. Upon receiving the query vector, he multiplies the encrypted query vector with the trained model, and here we depict only the portion of where the query vector is multiplied with class CJ. So here we have this one which multiplies the class probabilities, then those ones of the feature values, joint feature value for feature values, they multiply the conditional probabilities of class CJ with the corresponding feature values, so we multiply them. And this is the depiction only for class CJ, and the depiction for multiplying all of the query vectors with all of the trained model is shown over here. After we do the multiplication, then we run the secure sum protocol. That means at the beginning of the first slot of each query vector, we have the posterior probabilities for that class. And from now on, we basically run the secure max protocol to find the one which is with the maximum posterior probability. So basically now TAX randomly permutes those posterior probabilities. Then he uses the secure comparison of all data slots to compare their probabilities with each other and sends this result to the encryption-decryption server. By the way, the random numbers R1, R2, and K, etc. are sent from the user from the previous phase. So the user has only and knows those random parameters R1, R2, and K. Now, when the encryption-decryption server gets this result, he decrypts and decodes it and finds the random max index, the one that has the one where all the comparisons are positive, and sends this random max to the user. The user receives it in the fourth phase, runs the inverse ciphertext permutation, which can be run also not only on ciphertext but on indices, and finally gets the final classification result. This is the server-centric classification, where again phase 2 was run at TAX, phase 3 was run at the encryption-decryption server, and phase 4 at the user, as well as the phase 1 that we already saw. Something similar goes with the privacy-preserving user-centric classification. The only difference with the server-centric classification is that here the bulk of the computation is done at the user, while at the server-centric classification, the bulk of the computation was done at TAX. So, since we mentioned that during the user-centric classification, the user is a bit more malicious in a way that he executes the substitute then compare attack, in order to guard against this attack, at phase 1, TAX firstly randomizes the trained model in the following manner. So this is the trained model. For each of the class slots that keep the class probabilities, we put the same value, RC. And for feature value probabilities, among all of the classes, we put the same value. So value 1 of feature 1 at class 1 and value 1 or feature 1 at class CJ, and all other classes have the same random value put, and this is the case for all of the feature values among different classes. They have the same random value put in there. So APPENDIX randomizes the trained model in this fashion. It sends this to the user, and the user in phase 2 then does what we already have seen. So the user constructs the query vector that we saw, then the encrypted query vector, then multiplies this encrypted query vector with the randomly trained model, and finally he continues with the secure sum and secure permutation and secure comparison of all data slots, which contain now the posterior probabilities. Then sends these results to the encryption-decryption server, which in phase 3 gets this result, decrypts it, finds the maximum index, the one that has all slots, comparison slots, positive numbers, and sends this random index of the maximum integer back to the user. And since the user knows the random numbers k, r1, and r2, he can basically run the inverse random ciphertext permutation to find the actual index of the maximum integer, which basically is the class with the higher posterior probability to which the query belongs to. Here you have the codes for the privacy-preserving training and classification algorithms. So you have the corresponding header, the corresponding CPP, and the implementation for 3 different datasets. And as it was the case with secure building blocks, you'll also have those codes uploaded most probably to GitHub, and below you can find the corresponding link to download them. Setting the experiment environment. We are going to use 3 different datasets over here. We are going to use the SMS spam dataset, which is consisted of bigrams of consonants. Then for benchmark purposes and comparison purposes with other schemes, we're going to use the breast cancer Wisconsin dataset and the acute inflammation disease. And for homomorphic operations, we're going to use the Microsoft SEAL library. Here we give the experiment parameters, namely for polynomial modulus, we are going to use those moduluses. And for the plain modulus, we are going to use those plain moduluses in terms of bits correspondingly. So 27 bits is going to be for 4096 and 37 for 8192 and so on. And for the coefficient moduluses Q, we are going to use those coefficients in terms of bits respectively again. We give here the number of slots per class and query, the number of features, and so on for all of the data sets. And if we use the packing technique, if one query has NL slots, basically, having in mind the polynomial modulus, in one ciphertext we can pack this much queries, so to classify them simultaneously. Now let's see the experimental results and comparisons. So this is the confusion matrix for the SMS spam collection, acute inflammation dataset, and breast cancer. For the SMS spam collection, we use less number of attributes since we are using bigrams of consonants of SMSs, and we have similar accuracy than the state of the art. For the acute inflammation disease, for both the labels, we get 100% of accuracy, and maybe we are the only one to do so. So these are the confusion matrices for different data sets and their plain accuracies, and the privacy preserving accuracies are the same because there is no loss of accuracy due to implementing those classifications in privacy preserving fashion. Then we compare our secure building blocks with other state-of-the-art schemes, and in most, if not all of the cases, our secure building blocks outperform the others in terms of computation and communication cost. Okay, here we give the computation cost in milliseconds for different participants among different polynomials for the training, privacy-preserving training algorithm. And here we compare the computation and communication cost among different data sets and different schemes with our scheme, and our schemes outperform the others in terms of computation and communication cost. This is the cumulative communication cost for the privacy-preserving training algorithm. This is the communication cost for both privacy-preserving classification algorithms, and here we give the computation cost for them. Here we give, again, the computation per query, computation and communication cost per query. And if we compare them with other state-of-the-art schemes among different data sets and different schemes, again, our schemes outperforms the others in both communication and computation aspect. Finally, discussions and further directions. Here we propose some novel secure building blocks based on arithmetic circuits, which are flexible and can be used in different privacy-preserving algorithms, not only about machine learning. It can be data mining, graph theory, and others. We show that they are more efficient in terms of computation and communication cost, as well as general security characteristics than most of the other existing ones. We built privacy-preserving training classification schemes based on the Naïve Bayes classifier on top of them, and we implement in the future to add some new building blocks which were left here due to space constraints, and apply them to other frequently used classifiers such as support vector machine, deep learning, decision trees, and so on. In the end, we have an appendix where we deal with the malicious users for the server-centric classification stage. A malicious user is a user that can arbitrarily deviate from the protocol with the aim of fully or partially retrieving any information about the trained model. A malicious user, in our case, can perform several attacks. We give only 2 of them. And to avoid any attack, we should make sure that the malicious user behaves properly while executing the protocol. If the malicious user is not behaving properly, then we are going to abort the protocol. And what do we mean by proper behavior? Well, a proper behavior is considered the following. If for each feature fi, such as I goes from 1 to f, in exactly 1 slot per feature, the user puts 1 and the others are 0, then this is the desired behavior of the user. To make things simple, we are going to oversimplify this protocol. Basically, this is the malicious user query vector that is constructed at the user in phase 1. For each feature, we expect to put 1 at the corresponding feature value slot and everything else 0. If that's not the case, we are going to abort the protocol. And how we are going to see whether for each feature we have ones, where before continuing with the protocol, when the user constructs his query vector, we are going to find the sums for each feature using the secure sum protocol. If in the first slot of every feature we have value 1, that means that for all of the features there's only 1. For each of the feature there's only 1 slot that has 1 and the user is behaving properly. Otherwise, he's not behaving properly and we are going to abort the protocol. So that's the oversimplified statement of and the idea behind how we are going to deal with malicious users. For more details, you can check the pseudocodes and the manuscript with it. Finally, for the security analysis, to make things simple, very briefly, all of the data and information like frequencies, queries, trained models, and so on are in encrypted form, which are resistant to even quantum computers, or when they are brief in plain, they are randomized or blind. So this is the basic of our security. However, for more technical proofs and definitions, then we use the security definition under the semi-honest model to prove the security of our schemes, and more details are in the manuscript. This will be all for now. Thank you for your attention. See you next time.